Hello guys. So we're ready to start. So today we are starting actual calculus. Please pay close attention because this is going to get difficult and complicated. Easy school topics are over. Today's topic is the set of real numbers. So starting from this point and on, every definition I give you, every theorem I give you, you must be able to remember on the exam, and every theorem I prove, you also must be able to prove on the exam. So take notes, pay attention, and so on. So the set of real numbers. Definition. A set that I will denote with this letter R with an additional bar. R with an additional bar, like that. Is called the set of real numbers and its elements bless you. And its elements are called real numbers. If the following list of conditions hold, if the following list of conditions hold, the list of conditions is called the axioms of real numbers. Of the real numbers. So we will have a set that satisfies several, actually 16 axioms, and on this set we define two operations. I will call those operations plus and times are defined. And also relate operation less or equal is defined. And this set of elements and those operations satisfy the next 16 axioms. Those are actually the really simple rules of addition and multiplication and inequalities that you know from the school, except from the last one. The last one will be interesting. We will get to this point. So, number one, there exists such an element that we will call 0, such that for any real x follows x plus 0 equals 0 plus x equals x. For any real x, there exists an element that I will call negative x, such that x plus negative x equals 0. For any x, y, and z real holds that x plus y plus z equals x plus y plus z for any x and y reals. We have x plus y equals y plus x. So those are simple properties of addition. Now we have a similar set of properties of multiplication. Number 5. There exists an element that I will call 1, which is not the same as 0, such that for any x x times 1 equals 1 times x equals x. For any x except 0. This way I denote that I have some set, but I remove some elements from this set. So this is this set minus this set. So this is all real numbers except 0. So for any x except 0, there exists an element, I will note it as x power minus 1, such that also from real number, such that x times x power minus 1 x times y equals y times x. For any x, y, and z, well, it follows that x plus y times z equals x times z plus y times z. So those were the properties of multiplication, so to say. And now we have a bit more. Number 10. For any x, it follows that x is less or equal than x. So this symbol means and. This symbol means and. So for any two real numbers, from the statement that x is less or equal than y and y is less than equal than x, follows then x equals y. So this is the 11th axiom. So if two numbers are such that x less than equal than y and y less than equal than x, then this is the same number. Obvious stuff, I understand, but it's still important. For any x, y, and z, actually, let me change notation a bit. I'll write it differently. So for any x and y such that follows. The meaning is the same, but this notation I like better. So for any x and y and z reals such that x is less than or equal than y and y less or equal than z, from here follows x less than or equal than z. For any two real numbers, x less or equal than y or y less or equal than x. this symbol means OR. For any x, y, and z, such that x less or equal than y follows x plus z less or equal than y plus z. For any x, y such that 0 is less than x and 0 is less or equal than y, it follows then 0 is less or equal than x times y. Меньше либо равно, конечно, да. So those are really well known to you properties of those operations and the relation of inequality. Basically, you were taught about this in school. There will be another 16th axiom, so leave a bit of space in your notes. But let's discuss a bit those 15. So, from those 15 axioms, we basically can derive everything about arithmetics that you already know. For example, let me so a little bit of gap for 16th axiom. It will take a couple of lines. Let's try to prove something about arithmetics. We will not, of course, spend our time on proving everything, but we will show that it could be done. So, corollary. Corollary 1. There exists only one 0. So, over here, in the first axiom, I stated that there is a number 0 that satisfies this condition. Guys, masks. But what if there are more than one 0? What if maybe there are 2 zeros, or maybe even more. So let's prove it, that there is only one. Proof. Let and O2 be both zeros. Then let's look at this expression, 0, 1 plus 0, 2. Since 0, 1 is a 0, from the first axiom, it follows that this equals 0, 2. From axiom 1. But on the other hand, since O1 plus O2, let me write it like this. Since O1 is 0. But since O2 is 0, this equals O1. From axiom 1, since O2 is 0. Hence, O1 equals O2. So if we have any two numbers, any two elements that satisfy the first axiom, then they are the same element. Note that, yes, this is a very simple idea, and you already knew this way before, but this is still something that needs to be proven. Yeah? End of proof. Corollary 2. For any number, there is a unique negative number. For any real number, there is a unique negative. Let x1 and x2 be both negatives of x. Then x1 from the first axiom equals x1 plus 0, since x2 is a negative of x, I will write this 0 as x plus x2. Then using the third axiom, I can write it like this. And since x1 is negative of x, this first bracket is 0. And once again, from the first axiom, this is x2. So x1 equals x2.
And we solve it like we solved the upper one.
Once again.
Like we solved the previous one. Can we solve it like that? Like x plus x1 is equal to minus x plus x2 is equal to minus x.
Okay, yes, this is a good question. Let me. So, run me your name. Arvin. Arvin suggests this proof for this statement, a different proof. Please repeat.
X plus x1 is equal to minus x.
Equals maybe 0.
Oh, yes, 0, right.
Equals to 0, okay.
And x plus x2 is equal to
X plus x2 is equal to 0.
We can write from axiom 2.
Once again, from axiom 2, from here follows. What follows from the second axiom? No, this is not. No, this is not from axiom 2. This is by axiom 2. This is by definition of x1 and x2. By definition of x1 and x2. Okay, I agree.
We can equate them together and x will get x.
We can equate them together. Okay, this last step is a bit trickier. x1 equals x plus x2. I agree. The next step.
Then we can cut x by x. We can minus x from both sides of the equation.
Oh, yeah, understand. So you're saying that you can use which axiom? Yes, you can just to here add minus x, whichever it is. And from here you can say, we will see that this is x plus minus x, whichever it is, plus x1 equals x plus minus x plus x2. And since, I'll put brackets over here. And since this is 0 and this is 0, we have x1 equals x2. Yes, correct. I agree. Okay. Any more questions? Any more questions? Okay, moving on. Exercise. We will do this maybe on the seminars. Exercise 1. prove that for any real x, 0 times x equals x times 0 equals 0. Corollary 3. Yeah.
We can write it like x plus minus x is equal to 1 multiplied by x minus plus minus 1 multiplied by x. I won't show.
This is this. Well, I thought that we will do this during the seminars, but I think I heard what you're trying to say. I'm going to state this corollary, and then I will answer your question. So, statement: for any x, it follows that minus x equals minus 1 multiplied by x. This is not actually that obvious. I think you are using this statement in your proof.
I changed my mind.
You changed my mind. Oh, okay. We will do this on the seminars. Yeah.
By Exim 9.
By Exim 9. Okay.
Exim, when we will take 1 and minus 1,
Uh-huh.
get that it would be like.
Yes. I agree. We'll do this on the practical lesson. Actually, no. I'm going to okay, we will discuss your proof later. So, proof of this corollary. Let's construct this sum, x plus minus 1 times x. This is 1 times x plus minus 1 times x. Here by axiom 9 we have 1 minus 1 times x, and here this is 0 times x, and here from the result of this exercise that we will prove later, this is 0. Hence, minus 1 times x equals minus x. Exercise 2. Prove that 0 is less than 1. We will also discuss this on the seminars. Okay, so those 15 axioms are basic rules of arithmetics that you well know, and from here we can derive basically all of the arithmetics. I said that there is the 16th axiom. Let me write it down. I will call it the axiom of completeness, or the axiom of continuity. For any capital X and capital Y subsets of R. This symbol means subset. For any X and Y such that for any X from X and for any Y from Y follows X less or equal than Y. Actually, should it be strictly? No, less or equal is okay. And also, let's add condition that X is not empty set and Y is not empty set. So for any two sets like that, it follows that there exists a number C such that for any A from X, B from Y, it follows that A less than C less than Y. No. Less than B. You are, of course, familiar with the real line. Real line. So this statement has a good geometric interpretation. So this condition, well, X and Y non-empty, okay, this is easy. This statement, this part, says that the set X is to the left of the set Y. Sets could be very complicated in their internal structure, but this is to the left of that. So this statement says that this 16th axiom says that there exists a number between them. It seems kind of obvious when I draw it. Well, it is an axiom, so we are not going to prove it. But I'm going to note that this is not, generally speaking, obvious. For example, Exercise 3. Show that this 16th axiom, axiom 16, maybe I will call it differently. The axiom of continuity. Does not hold for the set of rational numbers. So basically, if here, everywhere, instead of the set of real numbers, we will put the set of rational numbers, they're not like this. Then this statement will not hold. Every other axiom, 15 first axioms, do hold. Can you see? We can add and multiply rational numbers and divide, and everything is okay, but not this 16. We will show it later. Well, on the seminars, probably. Okay. Some important subsets of set of real numbers. We have a set of natural numbers. This set is defined like this: 1, 2, 3, and so on. Where 1 is the one from the axioms, from the fifth axiom, where 2 I define as 1 plus 1, 3 I defined as 2 plus 1, and so on. That Z is a set of integers, whole numbers, integers. I will define it like that. Z is basically minus n, 0, and n. So this is a set that holds 0, 1, -1, 2, -2, and so on. Rational numbers. Those are numbers that can be expressed as P divided by Q, where P is an integer and Q is a natural number. And of course we have like different intervals. Like from A to B is set x such that less than x less than b, open interval b semi-open interval and so on. So this is the set of real numbers. We will also use so-called extended real numbers, extended real line. Definition. Extended real line I will call it R with a bar above, R with a bar. This is just R and two new symbols, that I will call minus infinity and plus infinity. This extended real line does not have well-defined, basically for real numbers everything works the same, but these new symbols do not participate in addition and multiplication, but the inequality is defined for them. It is defined like that. For any x from extended real line, well, basically let's from not extended real line, let's say that minus infinity is strictly less than x, or plus infinity is strictly greater than x, yes. We cannot add and multiply by infinities, but the inequality relation is defined. So this is real numbers and extended real numbers. Any questions? Questions so far? Moving on. Okay, moving on. This next topic will be called supremum and infimum. Supremum and infimum. Definition. A set X, subset of real numbers, no, subset of real numbers, is called bounded above if there exists a number C, real number C, let's call it capital C. Capital C, such that for any x from x, x is less or equal than C. Similarly, a set X is called bounded below if there exists a small c such that for any x from x, c less or equal than x. Definition is set x is called bounded if it is bounded above and below. Definition. Well, basically this number capital C over here is called an upper bound of my set X. Let me write it down. A number C is called an upper bound of a set X if for any x from x it follows that x less than or equal than C. Of course, we have a similar definition of a lower bound. Definition. A number C is called a lower bound if for any x from x, c less than x. Simple enough so far. Now we will have something interesting. Maybe I even should take a new board. Definition. A number, capital M, is called the least upper bound, or the exact upper bound, or supremum of a set X if the next two statements hold. First statement basically says that this is an upper bound for any x from x, x less or equal than capital M. And second statement says that any smaller number is not an upper bound. For any m dash that is smaller than m, it follows that it is not an upper bound. It is, let me write it down like this. M dash is not an upper bound. Leave here a bit of space. Let's discuss how to say, how to state this, that a number is not an upper bound. So here we have a definition that a number is an upper bound. For any x from our set, something happens. How to say that this is wrong? This is not will be a definition. Let's call it an exercise. C is not an upper bound. Let's say this. So, For any x, something happens. How to say that this is wrong?
There is an x such that it doesn't happen.
Yeah. We should write down that there is a number x of x such that this is not true. Such that x less than c is false. If x less or equal than c is false, this basically means x is greater than c. So there is x such that x is greater than c. So this is how we negate these kinds of statements. We will discuss more on the seminars. So let's return here, and I will write down this second statement again a bit differently. I will call it 2 with a star. This is the same statement. So for any m dash less than m, it follows that there exists x from my set such that x is greater than m dash. Correct? Similarly, we have a definition of an exact lower bound. A number small m is called the exact lower bound or infimum of x if first of all m is a lower bound, x is x, it follows that x is greater than m, and second, for any m dash greater than m, there exists x from x such that less than m dash, yes. Okay, now everything I said so far about bounded sets and bounds and the exact bounds I said about the set of real numbers. We can also extend those definitions to the set of extended real line. Not all of those definitions. The interesting point would be about bounds, upper bound, lower bound, and exact bounds, like those. So, for example, you can see that plus infinity, let me show you. Plus infinity is an upper bound for any set. Can you see? This is true. This statement is true for any real number. So plus infinity would be an upper bound for any set. And similarly, we can define supremum and infimum for that they could be infinities. Basically, all of everything I need to do is just to allow it over here. I will put over here, bar over here. So this number, capital M, for example, could be plus infinity, and then everything else is the same. Look, over here I didn't use any addition and multiplication. I only compared numbers, and we can compare infinities with real numbers. So this definition holds the same way. Okay, so basically I'm going to say that supremum and infimum could be infinities, and if I want to specify that this number is finite, I will just say so. Okay? Okay, moving on. What else do we need? Okay, moving on. So, okay, I have a question. What's upper bound or lower bound? Can you give an example of what is upper bound or lower bound? Yes, this is actually very easy to do geometrically. So if we have our number line, and this is our set X. By the way, by this picture, I do not mean to say that my set is an interval. I just mean to say that it is somewhere here. I'm not specifying the nature of this set. So, an upper bound would be, for example, this number, C, capital C. This is an upper bound of X. This is just any number such that any element from X is to the left. It's smaller. And, for example, this number would be an lower bound. And of course, you can see that I have like multiple upper bounds, for example. Yeah. So, for example, a number 2 is an upper bound of, for example, an interval from 0 to 1. Number 3 is also an upper bound. And basically, to specify the exact point where a number stops being an upper bound, we have this definition of an exact upper bound. And this number 1 is, it is also an upper bound, but this is the exact upper bound. This is the exact upper bound of an interval from 0 to 1. Okay? Questions? Questions? We will do this on the seminars, but okay. Basically, by definition, we should show that this is an upper bound, first statement, and then we should, for any m dash that is less than 1, give an example of an element from my set that is greater than m dash, by definition. Okay, any more questions? Okay, my time is almost up. The next thing I'm going to explain and tell you is the theorem. The theorem basically states that any set has a unique exact upper bound, but I'm definitely out of time for the proof, so I'm going to formulate and then prove this theorem on the next lecture. Guys, questions? Questions?
Actually, I have one. Can you come here? In the previous definition of bounded above.
Bounded above, I think it was here.
It's called bounded above C.
No, this is.
Whole set must be greater than C, right?
No. This set is called bounded above by C.
By C.
Yeah, so C is basically the ceiling. Okay, any more questions? Oh yeah. Can you also record the offline seminar class? No, Lan, you will have the class with Vera Markasheva. I have a question about Exim 16. If it doesn't hold for rational numbers, why don't we define it for irrational numbers? Okay. Onur asks if the Exim 16 doesn't hold for rational numbers, why don't we define it for irrational numbers only? No, you didn't quite understand it. The axiom holds for the set of numbers. It's not true that this is not the case that it holds for some numbers and not the other. It holds for sets. Okay, any more questions? Thank you for your time.